All right, guys, so today we're going to do in order what's on the slides. We're going to do number 8 on the worksheet together. That's not one you'll need to know how to do for testing, but it's a really good application, and it also involves some statistics regression analysis, which is actually a very usable skill. Then we're going to just have a very brief, oops, I started early, a very brief surface area of revolution discussion. I'm going to sort of explain. I'm going to show you what the formula is, and I'll briefly explain where it comes from. When we're done with that, I'll stop recording, and then everybody's going to go watch two surface area examples, a dx one and a dy one. I think they're each like 5 minutes long, a YouTube video on each, and then you'll finish up that surface area worksheet. There's 4 of them on there. The third one, I want to see if any of you can get it, but if by the end of the hour we're on the struggle bus, it's cool. It's you trying to derive the formula for surface area of a sphere by thinking of it as being a hemisphere revolved around the x-axis. Doesn't that make sense? So once we do surface area and you revolve a semicircle or a hemisphere about the x-axis, you would have the surface area of a sphere. It's a little harder than how they normally are because it's all in terms of variables. So you got to keep track of everything. I'm going to get you started with it and then let you go on your own. If you're super dependent on the key, I'll stop and do it. But you probably will finish in class today because we have a long hour and nothing takes particularly long. So the first thing up is number 8. So I'm going to have you take out your calculator and your worksheet. Number 8, 9, and the 4 surface areas are what are due today on today's Google form. So that's what I check tomorrow. So number 8 looked like this. So I'm going to do view full screen and head up front. So it's a bridge, Ben Franklin Bridge. And it goes across the Delaware River. It gives a center span of the bridge being about 4,200 feet. So you can kind of see on the picture. This line right here is the water level. So the bridge is secured 200 feet below the water level. We're going to use this as our center, all right? And that's the bridge cables, all right, that are swinging. And we're going to find the length of one of the cables. So our goal is to figure out the length of that red arc. Does that make sense? Well, you can't figure out its length. Let's go write the formula for that down. So if I want to know how much chain is needed, right, or what the length of that curve is, let's review. We integrate from a to b the square root of 1 plus the derivative of the function, either f prime of x or dy dx squared dx. Again, I write it every time because you need to memorize it and it helps. So what I need to do is figure out, we always start from the middle. I need to get the derivative of y. Well, I don't even have a function for y right now. But in the real world, when things look like something mathematical, you fit that something to the curve. You've done lines of best fit in Algebra 1 and Algebra 2. Do you remember doing those? Where you would plot the data and you'd be like, oh, I'm going to do a line of best fit here. That's what this is. I'm going to do a curve of best fit. What does this red chain piece look like mathematically? It looks an awful lot like a what? Parabola. So I am going to do, and a parabola is called a quadratic. So instead of linear regression, I'm going to use my calculator to fit an equation, a quadratic equation, to that curve. I don't know if you've done that in your other classes. I just know you've done linear. Later in the year, we'll do logistics, and that's actually the most common and applicable one in the sciences and the medical field and stuff, and biology. But what we do is we're going to, first of all, need some points. You need a minimum of 3 on the parabola, and 1 has to be the vertex, okay? So we're going to consider this the point 0, 0 for our parabola. So we're pretending it's laid out on a coordinate system with the x and y axis kind of going right through the center or the vertex of the parabola. So what we're going to do over here is go figure out this point and this point over here. Because the span of the cable is 4,200 feet, the x this way would be 2,100, and the x this way would be negative 2,100. Now I need to figure out the y. So somebody tell me how I'm going to get the y value of the points. And again, I'm considering this the origin. How will I get the y value? Go ahead, guys, you tell me. Yeah, we're going to subtract this 750 of the entire span and remove the water level. So 750 minus 220, 530, correct? Boom, boom. Now we're going to pass the buck to statistics, okay? And we're going to go enter that data. So you're going to go to your calculator. If you've had statistics, you probably remember. If you've had Algebra 2, I think they're working right now on a line of best fit. But it's pretty straightforward. What we do is we go to our stat button. So go ahead and press stat. You enter the data under edit. We need 3 points on our parabola. I have mine entered already. So 0, 0, 2100, 530, and negative 2100, 530. And let me know when yours are typed in. And any parabola can be written of the form, not y equals mx plus b, but y equals ax squared plus bx plus c. So we're in search of the a, the b, and the c. Just like for linear regression, you're in search of the slope and the y-intercept. So go ahead and enter it. Has anyone done this in a stats course or other class before? Do you know what you hit next? Anyone? Once the data's in? Stat. Yep. You go over to calc. You go down to quadratic regression. If it had looked like a cubic curve, I'd fit that to it. If it had looked like a quartic, I'd fit that to it. Natural log, I'd use that. I think the one below that, the 0 one, is our logistics. All right, so go ahead and hit quadrag, hit enter, work your calculator, bam. You won't need to know how to do this for the test. I'm just doing an application of the stuff you've been doing, because sometimes. So what I have here is that B is 0, C is 0, my R is 1, which is great. It means it's pretty much a perfect fit. Actually, that's R squared. I should have it so that the R comes up. That's called a correlation coefficient, and the closer it is to 1, the better of a fit it is. But I must have mine set to show. Are any of yours showing the R equals instead of R squared? No? Okay. Usually, you can program it. I'm not going to bother, but this is a very good fit is what this is telling me as a statistician. Does that make sense? All right, so I'm going to keep in mind that B is 0 and C is 0. So this is gone and this is gone. I'm going to go back up there and realize that I have y equals. Now what I'm going to do is store this because that's kind of an ugly number. So I think I'll store it in capital A on my calculator, just so that I don't have to keep rewriting it. So remember how to do that from years past. You just type it in. 1 point, can you guys read it to me because I lost it? 1.2018, 8, and then what? 14059. And then it was times 10 to the negative 4th, right? All right, so I'm going to go type that in, move it over. I'm going to store it. We did that a lot last year with our bounds when we were integrating. You can store it in any letter you want, but it might make sense since it's A to store it in alpha A. Then anytime I type A from here on out, I got it. Are we good? So that guy is stored. Now I'm ready to go figure out the length of that supporting cable on the bridge. All I need to do is, and I'll let you guys do it on your calculator, but I need to use my arc length formula for this curved function that I've just fit the curve to. So remember what I need to do. I need to integrate from where to where. In this real world problem, what are my limits of integration? Go ahead, guys, tell me. You guys are all in your calculators. Tell me what I'm integrating from. Negative what? 2100, yep, to positive 2100. Or if I was doing it by hand, remember last year I'd say you might want to choose to go 0 to 2100 and double it. But if I'm on a calculator, who cares, right? But keep that in mind for that number 3 that is a challenge problem. You might want to integrate from 0 to the radius and double it instead of doing negative r to r. You know what I mean? You might want to rotate half a quarter circle instead. It makes it easier because you'll be by hand. If you don't know what I'm talking about, I'm referencing number 3 on the assignment today. All right, so we do the square root of 1 plus the derivative squared. Remember, a in this scenario is a number, so my derivative is 2ax, right? And I need to square it dx. And now, just like you would do in the real world, you go to your calculator again. So you don't actually have to integrate these by hand in a real world context because things never work out nice. It's never like my a is 4. My a was 2.1 times 10 to the negative 4th. You know what I mean? That's why we've got calculators and we've got mathematicians, computer science people, calculus people who have programmed them. I don't know the answer to this, right? You need a math 9. Bring this in under the stored. If I remember right, it's 4,000 something, and I have no clue what the rest of it is. So somebody getting a 4,000 something, I'll steal it from you. Did you get it? Go to it. What's the question? Dinner, what's your question?
Oh, well, I just like the whole time you're talking, I was trying to figure out how to graph it on my calculator.
Oh, yeah, don't worry about that right now. You don't need to graph it. Can somebody tell me a final answer? What'd you get, Paulson?
4,300.
Can I have a backer? 4,372 feet. Let's just round it. I guess if I was getting cable, 4,307, I better at least get, that's round up in the real world. All right, so about 4,373 feet of supporting cable on the bridge. Does that make sense? When you do number 9, you're going to do it 2 ways. Do you see how in number 9 on your worksheet, if you were to go look at it, those of you at home, you can look at it, but it's got an actual function, e to the x plus e to the negative x, and then a parabola that's really close to it. And so you're going to use your arc length formula on the e to the x plus e to the negative x, and then you're going to use this process on a parabola. They're going to be really close, like the statistical fit and the actual function. All right, so next up, all we're going to do is ignore that. We're just going to do a quick surface area of revolution discussion. You don't even need to write it down. You'll need to take the notes, but for now, I'm just going to show you what's going to happen. So let's take maybe something kind of like this, a nice vase. And let's go from here to here. And you should know how to find the area of it. Let's call that base f of x, right? Area, y equals the integral from a to b, f of x dx, right? Revolve it left, you should know how to do. Right, you should know how to do. Maybe build up off of it with semicircular cross sections. Oh, that would be a good one, right? Do you remember the multiplier out front? What is it? For semicircle, pi-8ths, yeah. So we should know all that. But what we're going to do today, and you should be able to find the arc length of this outer function by using our arc length formula. Now what we're going to do is revolve it and not talk about the volume, but we're going to talk about its surface area. So the surface area, I'm still going to make this representative, but it's not going to be a rectangle. It's going to be that. Because when I revolve that little piece around, won't I get a little piece of the surface area? Wouldn't you agree? So let's think about that piece. It's got a thickness of dx, right? It's got this little piece, like it's 3-dimensional. It's got that little piece being the arc length, and then the other dimension is when it goes around. What are you looking at when I do this? Again, this is a real loose derivation, but when it goes around, what part of a circle are you getting? Circumference. Do you remember how to get circumference of a circle? 2 pi r, right? So in the formula for surface area, and that wasn't a proof, that was just so you could sort of visualize it, but there's a 2 pi out front. Okay, and you said 2 pi r, so there's an r in here. But you'll notice the r is this. Like if I whipped that around, that's the radius of that circle. Those of you at home, I'm whipping my arm around. It's really just the f of x, but we're going to write r. But point at it and write f of x. So it's 2 pi r. The other dimension was the arc length, right? So square root of 1 plus the derivative squared, and then we have the dx. So you don't need to memorize this, by the way. When I tell you don't have to memorize it, kind of what am I telling you? You will for me, but I'll let you write it down. Or I'll put it up on the board, and College Board won't test it. So, not because I shouldn't teach it, but they really try to minimize the amount of formulas that need to be memorized, and this one's kind of hard to remember. I always like to give you little mnemonics to help you. When I think of this one, I think of a pirate, and I think of 2 pi r arc length. See? And then I got it. So it won't be too hard to remember. Just think a surface area of revolution is the pirate. 2 pi r arc length. This is usually the f of x or the y value, right? It's how high it is. So if you were, say, revolving the square root function, and you wanted to find the surface area of the thimble, not the volume of it, you'd go 2 pi r, right? Arc length. See, it's not that hard. You know how to do everything in here. You take the derivative of the square root of x, square it, dx. And then if they tell you to go from 0 to 9, boom. So is there anything really difficult about the formula, Noah? No. You just have to know arc length, which I'm making you memorize, right? And you have to know the formula itself. Do you think these are primarily done on calculators or by hand? Calculators in the real world, but it's kind of fun to do them by hand. So on your worksheet, there's 3 by hand and 1 by calculator. All right, so that's it for the notes. For me, you're going to go watch and take notes on, because I do ask for them on the Google form. So if you want to grab a white sheet of paper, you're going to do 1 full dxer and 1 full dyer. I think there's like a 5-minute YouTube video for each one. So hop on to your, by the way, the guy on the YouTube video calls this y. He says 2 pi y because it's the y value. But I like 2 pi r because it actually comes from circumference, but there's a little bit of difference in our terminology, but the process is the same. So that's it. Those of you at home, you should be logging in, watching the dx video, write it down. The dy video, write it down. Those are very similar to the one I test you on for this, so if those make sense. I only put one of these on your test, and you don't need to memorize the formula. You need to primarily, actually, I'm going to tell you, I'll give you a dx one as well. So when that's done, go do the rest of the worksheet, and if you're stuck on number 3, let me know.